Oscillations. Introduction. The goal of this lab was to compare tracker data from a video to coding of the motion of a mass attached to a spring. Key concepts include Newton's second law, the velocity update formula, position update formula, and the energy in work principle. As you can see, below are the various types of energy, and above that is the formula stating that change in energy is equal to the work done by surroundings plus Q, thermal energy. Findings were change in total overall energy is 0, which is reflected by the changes in various other energies, and the observed and predicted motion of the mass are very similar. At t equals 0, the mass was at rest. However, it did have an initial position of negative 0.12 meters in the x direction and negative 0.63 meters in the y direction. The mass of the object was 0.402 kilograms. Here you can see the graphs and data yielded by the tracker of the x position versus time and y position versus time. Solve for k by using the formula for a period of oscillation and using the time of the period from the tracker data. You can rearrange the formula as seen below to solve for k. Solve for the relaxed length of the spring by substituting net forces acting on the mass during static equilibrium. Net forces acting on the mass include downward gravitational force and upward spring force. As you can see, the spring constant yielded was 6.83 and the relaxed length of the spring was 0.123 meters. You can see the conversion of the various physics equations and models used in this lab to code, such as various types of energy, gravitational force, and spring force. An important step is to ensure that the time step of the code matches the time step from the tracker, as to ensure that the data lines up when being compared. Here are the graphs yielded by the code. First, you can see the change in energy versus change in time graph yielded by the theoretical computational model. The next two are side-by-side comparisons of the x and y positions versus time of the data extracted from the tracker and the computational model. Discussion. Energy versus time graph. Gravitational potential energy and spring potential energy are inversely related. As the mass moves and the gravitational potential energy increases, the spring potential energy decreases, and vice versa. The mass's kinetic energy is smaller in magnitude than both of the potential energies, but adds together with both of them to result in an overall change in energy of 0. For the position versus time graphs, the x position versus time graph yielded by the computational model is more accurate to the experimental x position versus time graph than the computational model of the y position versus time graph is to the experimental y position versus time graph, which deviates slightly more. Some potential sources of error include not accounting for drag or energy loss due to thermal energy or other various types of energy, and inconsistent tracker data leading to unreliable spring constant and or relaxed spring length. What does it mean 1? Yes, the energy principle is satisfied because the total energy at any point in time during the mass's motion is 0. This is because the sum of gravitational potential energy, spring potential energy, and kinetic energy are equal to 0 at all times. What does it mean 2? Periods of oscillation based on the x position versus time graph and y position versus time graph are determined by analyzing the average time spent between the peaks or troughs. This yielded an average period of 1.65 seconds for the x graph and 1.38 seconds for the y graph. This makes sense since gravity does not act in the x direction, allowing for a larger range of motion, thus resulting in a larger period in the x direction.